Today I'm going to talk about a problem that you've definitely seen before, and this is the problem of finding the shortest path between every pair of points in a graph. So this is usually called all pairs shortest path. And I actually want to just look at a very special case here, and this is the case of unweighted graphs. So let's say that in my input, I have some graph G with vertex set V and edge set E. And this is an undirected graph, and it's also unweighted. So all the edges have unit weight. And I give you this input. You can have some time to process the graph, and then you have to answer a bunch of queries. So after this, I will have some queries, query 1, query 2, maybe query, I don't know, T. And every query gives you 2 vertices and asks for the length of the shortest path between these 2 vertices and also the shortest path itself. So the output is that for every query, let's say Q, which gave you 2 vertices I and J, you should output the distance. So write the, let's call it D, distance from I to J, and also print the shortest path. Or if there are multiple shortest paths, just print one of them. So write Dij and the shortest path from I to J. Okay, now here's the thing. As I said, I want you to have 2 different parts in the algorithm. So you will have a pre-processing phase. And this is when you've read the input, you've read the graph, and you're just doing some algorithms, maybe keeping track of some values so that you can answer the queries faster later on. And then there is a query phase. And in the query phase, you will just get the queries one by one, and you have to answer them in the order that you get them. Now, here's the thing. I want my pre-processing to be as fast as possible. Okay, but the constraint is on the query side. I want to say that if the distance from I to J was, let's say, D, you have to answer that query optimally. So what does that mean? When I'm given vertices I and J, I have to output D+1 numbers, right? So the first number is the distance, and then I have all the vertices that are on the path from I to J, right? So I have to output D+1 numbers, and I want to be able to do that in linear time in terms of the output. So when I do a query that gives me I and J, this should be answered in O Dij, where Dij is the distance from I to J. Okay? So you can do whatever you want in the pre-processing, but the query has to be optimal. This is the problem. And of course, when we use randomization, then here I can have expected time. So if I have a randomized algorithm, then I want every query to be answered in this much expected time. So if I use randomization, this is not a worst case, this is just an expectation. Okay. So how can we solve a problem like this? You've probably seen in undergraduate algorithms courses that we can just pre-process everything, right? So a very simple idea would be that I take every one of my vertices and I just do a BFS from that vertex. And I can't do a BFS because I don't have weights on my edges. So I take vertex 1, let's say, and I do a BFS from this vertex. And this gives me a BFS tree, right? So something like this, and then it will go. Okay, so if I do a BFS from vertex 1, that gives me a BFS tree. And then I know that the shortest path from vertex 1 to every other vertex is just the path that goes through this BFS tree, right? So I can simply do a BFS from every vertex in my pre-processing and keep track of these BFS trees. And then whenever I get a query ij, I just go to the BFS tree of vertex I instead of vertex 1. And I just print the path that starts here and goes to vertex j, right? So how much time would this take? How much time do I need for my pre-processing? And let's say that I have n vertices. So in the worst case, I'm going to have edges between every pair of vertices. And a BFS takes linear time in the number of vertices plus the number of edges. So every one of my BFS operations is going to take n squared. And I'm doing n of them. So my pre-processing is going to take cubic time. Now, but do I satisfy this constraint that every query is answered optimally? Yes, because whenever I want to answer a query from I to j, I just go to the BFS tree that I created for vertex I, and I just index into vertex j, and I start from j, go all the way back until I get to the root, which is I, and then just print that. So yeah, the query part is optimal. Nice. But what else can we do? What other algorithm do you know that would work in a similar way? So we also have the Floyd-Warshall algorithm, right? And that one also has a similar runtime. So if you look at the Floyd-Warshall algorithm, hope it was 2 L's. What was the idea there? The idea there was that we do a dynamic programming, right? So the idea was that I can define some dynamic programming variable, let's say dijk, and I can say that I want this to be the shortest path between I and j that only uses the first k vertices. Okay, so this is actually the length of the shortest path from I to j, only using the vertices from 1 to k as internal vertices in my path. Okay. And then we had a very simple recursive formula for this. So let's say that I want to go from vertex I to vertex j, and I can use the first k vertices. There are two cases. Either I use this last vertex, vertex number k, or I don't use it. If I don't use my last vertex, then all I get is the distance that I could get with the first k minus 1 vertices, right? And if I use the vertex k, then I have to start from I, and I have to go to k. And then from k, I have to go to j. But the internal vertices here are all between 1 and k minus 1. And the internal vertices here are also all between 1 and k minus 1. So what I get is d of I k minus 1 plus d of kj k minus 1. And so I have two cases, and I want the smallest of the two, so I just take the minimum. Right? So I compute every one of these variables that I had in my dynamic programming in constant time, because these are a constant number of operations. So my runtime would just be the number of variables that I have, and that's n cubed. And actually, this is like one of the simplest algorithms to implement because you can just write 3 nested for loops, right? And actually, in implementation, we usually don't put k there at all. So in implementation, we would usually just do something like this. We say for every k from 1 to n, for every I from 1 to n, and for every j from 1 to n, the distance or that variable from I to j is just the minimum of what it was before, d of ij, and d of ik plus d of kj. So this is like one of the simplest algorithms to implement. It's literally 4 lines. Okay? So I'm just thinking of it here. I was thinking of the shortest path from I to j that only uses the first k vertices as internal vertices. But I can just say I don't care about the k, and I say d of ij is the shortest path from I to j that I have seen until this point of my algorithm. And I know that until this point of my algorithm, I've processed the first k vertices. So I can get rid of this last index here, and I can write the algorithm just like this. Okay? But now, if I do this pre-processing like this, if I do this Floyd-Warshall, again, my runtime is going to be NQ, which is the runtime that you can also get from these 3 for loops. It's very obvious. But how about querying? Well, when I do the query, I have to write the distance, and I have to also write the shortest path. So writing the distance is easy. But how do I find the actual path? Well, I just have to keep track of how I updated my variables here. And I have to keep track of what was the last vertex that I used as an internal vertex between I and j. And then I know that I have to go from I to that vertex and then from that vertex to j. So if I just keep track of which values of k actually updated my value here, gave me this minimum, then I can easily find the path itself as well. Okay, but this is still not good. So we have our optimal querying, but our pre-processing is still cubic. So this is not better than just doing BFS. Of course, this algorithm also works if you have weighted edges, but in our input, we said that we don't have weighted edges. So for our particular problem, this algorithm is just as bad as doing n different iterations of BFS. But now what I want you to see here is that this is some sort of a matrix multiplication. If you look at it more carefully, or actually, if you look at this one. So it's very similar to matrix multiplication, except that I have addition in place of normal multiplication, and I have the minimum operator instead of normal addition. Okay? So I don't want you to read too much into it right now, but basically my point is that it's very natural to think of these things in terms of matrices. And that's what we're going to do. So I'm just going to try to formulate everything in terms of matrices. And let's erase this one. And another thing is that we generally got the shortest path for free. So in both of these cases, the hard part was finding the distance. And after you knew the distance from I to j, actually finding the shortest path, that wasn't much work, right? So I'm going to separate these two problems, and I'm going to call them the distance problem and the shortest path problem. So when I talk about the distance problem, I just want to write this distance. When I talk about the shortest path problem, I want to also write the shortest path itself. Okay, so let's first try to just take the distance part and forget about outputting the shortest path, and let's see if we can do it any faster. Now, this is the part where I want to use the idea that we saw actually in skip lists last time, which was that there we had some linked list. So you can think of a linked list as a graph, right? It's just that it's a path, right? And then we created another linked list. And the idea in the other linked list was that it could basically jump 2 steps to the right every time. Okay? So let's see what happens if I apply this to a general graph. So, and I want to use a matrix notation. So let's say that this is my graph G, which was given to me in the input. And I want to have 2 matrices. There is a matrix A, which is the adjacency matrix of G. So A is just an n by n matrix, and Aij is 1 if there is an edge from vertex I to vertex j, and it's 0 otherwise. So I can use this matrix to show my graph G, of course, because it tells me which vertices have edges between them. And what do I want to find? I want to find a matrix D, which is also n by n. And basically, I want Dij to be the distance or the length of the shortest path from I to j. So Dij is distance from I to j. Now, so I'm given A in the input. I want to compute D. And of course, I want to do it in faster than n cubed, because n cubed was what we had already. Now, let me erase this. How do we apply our skip list idea? So I want to create another graph. Let's call it G2. So I write it like this. And what I want is something like this. I want to say that if there are 2 vertices, let's say I and j, in my graph G, such that there is a path of length 2 between them. Okay? I want to just have a direct edge between I and j in this graph. Okay, so I want to basically have a shortcut so that when I want to go from I to j, I don't have to pass through both edges. I can just take one edge. And actually, I want to even have this if the distance between I and j was already 1. So if they were already connected here, I will also connect them. So to be more specific, Ij is an edge in this new graph in G2 if and only if the distance between I and j was at most 2 in the original graph. So the distance in the original graph is the matrix D, which I have to compute it, but I just use it right now without computing it, if Dij is less than or equal to 2. Okay. So I want to compute this graph from my original graph. It's not too hard to compute this, right? So how would you do this? How would you compute this graph from the original graph? So when are I and j connected in this new graph G2? For them to be connected in G2, either they should be connected in G or they should have a common neighbor in G. So it's that either they're directly connected here in G, or they have a situation like this. And let's call this vertex K. So I can just go over all of the possible vertices K in my original graph G and I can just connect all of their neighbors. So I take every vertex that is like K there, and let's say it has a bunch of neighbors. And I just connect all of its neighbors. Right? And this would give me the graph G2 that I'm looking for. And again, we are showing our graph mostly with its adjacency matrix. So I can say I have a matrix A2, which is also n by n. And this is the adjacency matrix of G2. And again, I can compute it in the same way. Now, how much time do I spend to get to G2 from G? So G was given to me in the input. I'm creating G2. How much time am I spending? It's n squared, right? Because I'm taking every vertex. Oh, okay, no, it's not so good. So I'm taking every vertex K, and I'm looking at every pair of its neighbors. So in the worst case, this is n cubed, right? Because I can have n different choices for K, and maybe the degree of K is large. Maybe I have a lot of neighbors, and then I have to take every pair of neighbors. So this is not good. Can we compute this thing faster? So just think about matrix multiplication. And you know that matrix multiplication can be done in a time that is less than n cubed. Okay. So what happens if I just take this matrix A and multiply it by itself? Right? So if I just take A squared, which is like A times A, and not necessarily the same as this. Okay? What does this matrix give me? So A squared of ij is just the sum of aik times akj for every k. Right? So this is the, and aik is 1 if I have an edge from I to k. So a squared ij would be non-zero if there is a k like this. And it would be 0 if I don't have a k like this. So I can just compute this a squared, and then I can just do a pass over it and turn all of the non-zero elements into 1. Right? And then that would give me this A2. So these two are not exactly the same matrices, but they're quite similar. Okay, so how much time do I need to compute A squared? Well, I'm multiplying two n by n matrices. If I just use the naive way of multiplication, I will again get n cubed. But actually, you know that there is, for example, Straussen's algorithm that does this much faster. And actually finding the best algorithm for multiplying matrices is something that people are really competing about. And there is this concept of omega, which is the matrix multiplication constant. So this omega is the matrix multiplication constant. And the way it's defined is that it's the smallest value such that you can do matrix multiplication in n to the power of omega. And we don't know the exact value of omega, but we know that as of 2020, omega is at most 2.373. So someone has come up with algorithms, with an algorithm that would multiply two n by n matrices in n to the power of 2.373. Okay? And again, we don't need to know that algorithm. We don't need to implement it. We just use it. So I do n to the power of omega to compute this a squared. And after I compute this a squared, the conversion to the adjacency matrix of G2 was just going over all the elements once and taking any element that is non-zero and turning it into 1. So that part is like n squared. So overall, the time it takes for me to compute G2 from G is at most n to the power of omega. Okay, nice. But what can I do with G2 now? So G2 is the same graph as G, except that I now have these shortcut edges. What can I say about the relationship between distances in G2 and distances in G? So let's say that I also have a distance matrix here. I call it D2 n by n. And again, I don't have the D matrices. I have to compute them. But for now, I'm just doing mathematics over them. So I just want to reason about their values. So what can I say about D2 of ij? So the distance between the vertex I and vertex j in this new graph. So let's take the original graph and let's say that I had vertex I, and let's say this was the shortest path that got me to vertex j. Okay? And for example, let's say that this path had length 10. Okay? In this new graph in G2, I have a bunch of shortcuts. So every two edges now have a shortcut that just goes directly. Right? So like this. So I know that if in the original graph my distance was 10, in this graph my distance would be 5. Right? What about if my distance in the original graph was, let's say, 9? Then again, the same thing happens, but I can't take the last shortcut. So I have to go 8 edges with these shortcuts, with 4 shortcuts, and then I have to take the last edge from the original edges. So if the original distance was 9, the distance in G2 would again be 5. Okay, so I have two cases. I can say that if the original distance from I to j is even, then this distance would just be half of it. So if it's even, then the distance from I to j is just twice the new distance from I to j. But if this distance was odd, then the distance from I to j in the original graph is twice the distance from I to j in this new graph plus 1. Okay? Yes. No. So we keep all the edges of the original graph as well. Right. Okay. So you're correct. So when we multiply them, we should also again add a so that we have the edges of the original graph. Yes, I didn't remember that. Yes, but anyway, the way I'm defining G2 is that I have an edge if I had the edge in the previous graph or if I had a path of length 2 in the previous graph. Okay. Yeah, so G2 is not, so this matrix is not exactly this one squared. We have to square it. Then we have to add it itself to the square. And then we have to do the processing where we took everything that was non-zero and turned it into 1. Okay. But again, the runtime still remains n to 2. Okay, now I have these things. So what I want to do is that I want to just recursively compute this one because I think that computing this one might be easier. And then having the distances in G2, I want to come back and somehow find the distances in my original graph G. Right? Now, how do I do that? Well, I just take this G2 and do the same thing again. Right? So I'll get something like G4, let's call it. Right? And then I'll get G8 and so on. And I continue this until at some point, my graph just becomes either a complete graph or all of its connected components become complete, right? Or another way of looking at this is that the distance between every pair of vertices is at most n. So I can just do this operation log n times, and I will eventually get to a graph where all the distances are either 0 or 1, right? And then at that point, I have this distance matrix. So that's like the D, but this thing here is like n, right? Because I did this log n times, and every time I'm multiplying. Okay. So at some point, I will have this matrix, but the problem is, how do I go back? How do I go from having distances in G2 to having distances in G? Because if I can solve that, then I have a recursive algorithm. Okay? So let's say that I've magically given you this matrix. So you know the distances between all the pairs of vertices in G2. How would you compute the distances in G? You see, the problem really is to figure out which distances are odd and which distances are even, right? Because if I know that Dij is even, and if I have this other matrix, then I can easily just use this formula. And the same if I know it's odd. So I somehow need to be able to decide if a particular distance Dij is odd or even. So let's see what we can say about Dij. First, just assume that Dij is even. Okay, so in my original graph, oh, and I'm going to draw the original graph in black and this second graph in red. Okay, so if Dij is even, I had a situation like this. I had my vertex I, and let's say this was the shortest path to the vertex j, and its length was even. So let's say the length was 2n. Okay. Now I just want you to look at all of the neighbors of I. So let's say that I take a neighbor here. Let's call it, I don't know, t. Now, what is the distance from t to j? There are two cases. Either the shortest path from t to j is to go to I, in which case the distance from t to j is going to be 2m plus 1. Okay? So the distance from t to j can be 2m plus 1. Or actually, I was supposed to write it like this. Okay, what other values can it have? It might be that there is another shortest path that goes from t to j, and that one also has 2m edges in it, right? That's also fine. So the distance from t to j can also be 2m. Can it be 2m minus 1? Yes, because it might be that t is basically right here on the shortest path from I to j. Or maybe there are many shortest paths from I to j, and at least one of them goes through t. So this distance can also be 2m minus 1. But can it be anything smaller than that? No, because if this one was less than or equal to 2m minus 2, then the shortest path from I to j would be to just go to t and then go to j. And that would mean that the shortest path from I to j is not 2m. That's not acceptable to us. Okay. So what can I say about the distance from t to j in the other graph? So what can be the d2 from t to j? Let's just use this formula, right? So if it's even, you just divide by 2. If it's odd, you divide by 2 and add 1. So dtj can be either, so in this case, it's m plus 1, or m, or again m. Right? So the distance from this neighbor to this vertex j in this graph is going to be either m plus 1 or m. Now, what was the distance from I to j in this graph, in the second graph? It's just m, right? So what I just proved is that if the distance from I to j in my original graph is even, then for every t that is a neighbor of I in my original graph, the distance from I to j in this second graph is less than or equal to the distance from t to j in this second graph. Okay. Nice. Now let's do the same thing, and let's say that the distance from I to j in the original graph was odd. Again, I want you to look at the same thing there. So I have I and I have j, and this was the shortest path between them, and the length was 2m plus 1. Or actually, let me say 2m minus 1, so that. Okay. Again, look at the neighbors of I. So let's say I have a vertex t here, and t goes to j. So what are the possible values for the distance from t to j? Again, I can do the exact same argument as before. It's either 2m minus 1, or 2m, or 2m minus 2. Right? So now if I look at the distance in the other graph, d2 of tj, what distances can I have there? Well, this is just m, m, and m minus 1. Okay? So if the distance from I to j is odd, then I can say for every t, which is a neighbor of I in the original graph, the distance from t to j in the new graph is less than or equal to the distance from I to j in the new graph. Okay. So I have all the distances in the new graph. I have this matrix. Can I use just these ideas here to compute this one? Not necessarily, right? Because I might have a situation where I have some vertex I, and the distance from I to j here is the same as the distance from all of the neighbors of I to j. Okay, so I have to still do a little bit more. Okay, let's go back to this picture. So I'm taking all of the neighbors of I, and those were the t that I was looking into. But there is a particular neighbor that is on this shortest path from I to j. Let's call that one t star. So let's say this is t star. Okay? What do I know about t star? I know that from t star to j, I have 2m minus 2 edges. Right? So t star is in this case. So I know that there should be at least one neighbor of I that has distance 2m minus 2. So there should be at least one neighbor such that the distance in this second graph is m minus 1. So I can extend this one, and I can say for all the neighbors, the distance is less than the distance from I to j, and there is one neighbor, let's call it t star, such that the distance from this neighbor t star to j in the second graph is strictly less than the distance from I to j in the second graph. Okay, now I can reconstruct this matrix from this matrix, right? because I can just take this matrix, D, and I can say, okay, here's the thing. Let's say I want to compute Dij, the distance from I to j. I just look at all the neighbors of I, and if I found one neighbor like this, such that the distance from that neighbor to j was less than the distance from I to j in the second graph, then I say Dij has to be odd. And as soon as I know it's odd, I have a formula for it. Otherwise, I say it's even. And again, as soon as I know it's even, I have a formula for it. Okay, but now how much time am I spending on computing Dij from this matrix D2? Okay, again, the problem that we have is that we're going through all the neighbors of I. Right? And that's not great. Because you see, I want to compute Dij. There are n squared different values that I want to compute. And for each one of them, I'm going over all the neighbors of I, which can be up to n. So I'm spending n cubed time again. But again, our technique is going to be the same. Can I somehow write this as a sort of matrix multiplication? Because I know that I can do matrix multiplication faster. Okay, so let's just write this. Dij, let me see. What happens if we just sum all these distances over all of them? So let me just take this idea here, and instead of talking about every single one of the distances from the neighbors to j, let's talk about the sum of distances, because that's something that I would be able to probably write as a matrix multiplication. So I want the sum of the distances from t to j, where t is a neighbor of I. So I'm not going to write it anymore. Whenever I say t, it's going to be a neighbor of I in the original graph. Okay? And if this sum is greater than or equal to the degree of the vertex I times the distance from I to j, then I know that the distance from I to j in the original graph must be even. Right? And if this sum is less than the degree of I times distance from I to j, I know that Dij must be odd. Okay, this is nothing special. I'm just saying that if the distance from I to j in the original graph was even, then in the new graph, the distance from I to j would be less than or equal to the distance from any one of the neighbors of I to j. So I can just sum them up, right? And if I sum them up, on one hand, I get the degree of I times the distance from I to j in the new graph. On the other hand, I just get the distances from t to j, right? And the same thing here. Here, if the distance from I to j was odd in the original graph, then in the new graph, I know that the distances from all of the neighbors to j is less than the distances from I to j, right? But there is also at least one single neighbor where this distance is strictly less. So if I just sum all of these distances, it would be less than the degree of I times the distance from I to j. That's all I'm writing there. Okay, but what does this tell us? It tells us that if we can compute these sums, then we can just apply these rules, right? So let me just have some new n by n matrix, let's call it B. And I want to say that Bij is just this sum, is the sum over all t's that were neighbors of I in the original graph of this thing, the distance from t to j in the second graph, which is from this matrix. Okay. Can you see a better way of writing this so that it looks like matrix multiplication now? So can I just say that B is just A multiplied by D2? Yes, because if I just multiply A and D2, what do I get? I get that Bij is the sum over, let's call it T now, of AIT times DTJ2, okay? But AIT is just a Boolean value that tells me whether I and T are neighbors. So this is the same as saying I'm taking this sum over all the neighbors. Okay, nice. So now if I have this D2, I can just multiply A and D2 and I get this new matrix B. And I'm taking order n to the power of omega to do that. But now from B, I want to get back to this matrix D, but that's quite easy. I just go over every one of the entries of B and I see if this inequality holds or this inequality holds. And that tells me whether the distance should be odd or even. And then the distance here is always twice the distance here, and I just have to fix the parity, odd or even. So all of these things are going to take n squared time. So given the solution for G2, I could find the solution for G in O(n) to the power of omega, because everything else I did took n squared, and omega is more than 2, at least for now. So I've done all of this in n omega. Nice. Now let's go back and let's complete our algorithm. So what is our algorithm now? Our algorithm is that I have this graph G. I first compute G2, right? Then from that, I compute G4. Then I compute G8, and so on, until I get to G, let's say 2 to the power of k, where this 2 to the power of k is more than n. So at the point where I get here, I know that the distance between every pair of vertices is now either 0 or 1, right? So I can easily find the distances in this 2 to the power of k thing. I can find this distance matrix here, right? Because this distance matrix is basically the same as the adjacency matrix at this point. Then I start from here and I go back. So I have the distance for this graph with index 2 to the power of k. I find the distance matrix for 2 to the power of k minus 1. And I do the same until I find the distance matrix for 4. Sorry, this corresponds to this, yeah. And then I find the distance matrix for 2, and then finally I find my original distance matrix. So this is how my algorithm would work. It's basically recursive. Now, how much time am I spending? Well, every time when I go from G to G2, I'm spending n omega. And again, here I'm also spending n omega and so on. So every edge that goes down is spending n omega. And when I come back up, again, I'm spending n omega, n to the power of omega at every edge. Right? So what is the depth here? The depth is log n. So my overall runtime is just O n omega log n. So using matrix multiplication, we could finally get something that is better than n cubed. Right? Now, I have this thing that is better than n cubed. And I can use it as my pre-processing. So let's go back to our original problem again. Our original problem was that I'm given a graph and I have to answer a bunch of queries. So I can do this pre-processing and it's much faster now. But how do I answer the queries? When I'm given two vertices I and j, I can just look up their distance from this matrix that I've computed. But how do I find the path itself? Now that's the part where this whole idea of matrix multiplication really fails us. So if you just want the distances between every pair, this is going to work and it's faster than the previous approaches. But now let's say I want to also find the path itself. Okay, so the rest of this lecture and probably even some of the next lecture is about finding the path. And by the way, we haven't used any randomization until this point, right? So since we are in the randomized algorithms module, you would expect that I would use some randomization. Okay, but for now, I want you to just save this information somewhere in your memory, and I'm going to switch to a different problem. And somehow that problem is going to help us find the paths in our original problem later on. So let's just talk about a different problem. I'll get back to the original problem later. What? No, I think. Oh, this one. Yes. Yes, sorry. This one is -1. Yeah. I'm not very careful with these things. Okay, at least we now have a better solution for all pairs distance, not for all pairs shortest path. Okay. So I'm going to do a lemma, but I don't want to give you the proof of it because it's just a lot of algebraic works. But I'll give you the intuition for this lemma. And you should be able to prove it using tools that we've already seen. So let's say that I have n balls in a bag or in a bin. So let's say we have n balls in a bin. And let's say that some of these balls are white and some of them are black. So W balls are white and n minus W, which I also call it B, balls are black. Okay. So here's what I want to do. I want to choose some number of balls. Let's say I want to pick k balls randomly. And I want to do it so that I have exactly one white ball. Okay? With some good probability, of course, because I can't guarantee it. But intuitively, how many balls should I take to expect that I have exactly one ball, one white ball? So I have n balls overall, W of them are white. Okay? So it's kind of obvious to say that we expect to take something like n over W balls, right? So my goal is, again, my goal is to take, let's say, R balls randomly so that exactly one white ball is taken. And I don't want more than one, I don't want less than one. And of course, I want this to happen with some probability. So let's say with probability at least something, some constant. Okay? So since I want to have exactly one white ball, it seems kind of obvious that I should take almost n over w balls. So here's the lemma that I want, which actually makes this a little bit more precise. And the lemma is this. Let's say that we take R balls uniformly at random and also without replacement. So when I take a ball, I wouldn't put it back. I just take more balls. Okay? Now the lemma is that if I have this inequality, which basically means that I'm almost taking n over w balls, right? So I can write it like this. If I have this inequality, then the probability that I have one white ball is going to be high. Then the probability that I have exactly one white ball is actually greater than or equal to 1 over 2e. Okay. So again, I just want you to see the intuition because I don't want to do the algebra. The intuition is that this is the fraction of the balls that are white. On the opposite, sorry, w over n is the fraction of balls that are white. So if I just want one white ball, I expect to take n over w balls before I see my first white ball. So now I'm saying I'm taking r balls, but r is kind of close to this number. So it's between this number and half of it. So I'm almost taking the number of balls that I would need to see exactly one white ball. And then I'm saying that the probability that I see exactly one white ball is more than 1 over 2. Now, we can actually compute this probability exactly. And I'm going to do that, but I'm not going to do the algebra that shows that this is more than 1 over 2. Okay. So what is the probability? Again, I have n balls. I'm taking r balls. And I want to see what is the probability that exactly one of them is white. So if I want exactly one white ball, I have to first choose my white ball. And then I have to take the black balls. And from them, I have to choose the rest of my balls, r minus 1. So these are the number of cases where I get exactly one white ball. What is the total number of cases? Well, I'm just taking r balls from n balls. Okay? So this is the probability. But again, you can just write this, expand it, apply this idea that n minus w is b and so on, and then differentiate it and do everything on it, and then finally show that this is going to be more than 1 over 2. I'll probably give you a link to this on Canvas, but I'm not going to do it. Okay, so just agree that this holds. Okay, now I'm going to use this for a completely different problem. And this problem is also some sort of matrix multiplication. But it's what we call Boolean matrix multiplication. Okay, so let's say I have two matrices, A and B, and let's say that they are both n by n, and I want to multiply them. But let's say that in these matrices, all the entries are either 0 or 1, true or false. And when I'm doing the matrix multiplication, I'm using and or instead of multiplication and addition. Okay, so let's say that C is A times B. Normally, if I was working with integers, I would just say that Cij is the sum of Aik times Bkj over all k, right? But now I want to work with Boolean values. So I want to say that Cij is, instead of taking a sum, I just take the OR over every k. And then instead of multiplying, I just take the AND. Okay? Now, this is called Boolean matrix multiplication. And of course, you can solve Boolean matrix multiplication using normal matrix multiplication. So just imagine that these zeros and ones, instead of being Boolean, they're actually numbers. And then do this multiplication. And then just take anything that is non-zero and turn it to 1. And you will get this result. Okay? But I want you to focus on this one. So when is Cij equal to 1? So in order for Cij to be 1, okay, so how is Cij obtained? I'm taking my matrix A, and I also have my matrix B. And I'm basically taking row I of A and column J of B. So let's say I'm taking this row I, and I'm taking this column J. And now what am I doing? I'm just going over them and seeing if there is an index K, so that I have a 1 here and also a 1 here. So I want to have a 1 here at index K. And I also want to have a 1 here also at index K. Right? If I have a situation like this, then Cij would be 1. Otherwise, Cij would be 0. So I call this K a witness for Cij. So whenever I say I want a witness for Cij, I mean a K like this. And the reason is because it basically proves that Cij has to be 1. So it's witnessing or proving the fact that Cij is 1. Now, here's what I want you to consider. Let's just assume that every Cij that is 1 has a unique witness. So I just want you to assume this for a second. So assume all witnesses are unique. So I've given you these two matrices in the input, A and B, and I'm just telling you that I know that if you multiply it, the witnesses are going to be unique. And I just ask you to give me all the witnesses. So I want you to output some matrix W such that Wij is the unique witness of Cij, if it exists. And of course, if Cij is 0, you can just output 0 for Wij. I don't care about that. Okay? So again, we can have an algorithm that does cubic time, right? For every I and j, I can go over every k. So I can go over here and see if I can find a 1 at the same position. And then if I found that, I say, this is my witness, n cube. Can I do better than n cube? So again, the idea is that you have to somehow turn it into matrix multiplication. So here's what I would do. I can take my matrix A and I can change it. So let's say that I create a new matrix. Let's call it A bar. Okay? And I just say that A bar of Ij is going to be J times A of Ij. So remember, A was a binary 0, 1 matrix, but now A bar is a matrix that can have any number in it, any integer in it. And all I'm doing is that I'm multiplying it by J, right? So in other words, I'm just taking my matrix A and I'm saying, take column 1, multiply that by 1. All the elements in column 2 get multiplied by 2. All the elements in column 3 get multiplied by 3, and so on. So now what happens if I multiply this matrix, A bar, with B? Okay? What happens? So let's call this, I don't know, let's call it C bar. Let's say C bar is A bar times B. So what is C bar of ij? So just let's go with the definition. So I'm starting here at row I, and I'm starting here at column J, and I'm just going forward. And all of these elements are 0, right? So when there's 0 in A, there are also 0 in A bar. Until at some point I get to a witness. But when I get to a witness and it's at index K, here I have a 1, but here when I did A bar, I multiplied it by K. So Cij is just K, it's that witness. So if I have a unique vertex, if I have a unique witness for every Cij, then this multiplication just gives me all the witnesses. Okay, nice. So if I assume all the witnesses are unique, I can find all the witnesses in n to the power of omega time. Oh, so this is the same matrix as A, but I'm just taking the first column, I'm multiplying everything in it by 1. The second column, I'm multiplying everything in it by 2, and so on. So I'm saying if I have a unique witness, then this witness which was here, instead of 1, it becomes a K. And here I didn't change B at all. So when I multiply, I will just get the index of that unique witness. So I get the indices of all of my witnesses really fast. Okay, now I want to get rid of this assumption. Now I want to say, don't assume this. So you can have multiple witnesses for every Cij. And what I want, again, is for you to give me a witness matrix like this. And the witness of ij should be one of the witnesses that show that Cij should be 1. Okay? So if I have several choices, I want you to give me one of them. Now here, there would be a problem if I do the same thing. Right? Because I basically get the sum of all of my witnesses. Right? So if I have, for example, let's say I have 2 witnesses. Let's say I have K1 and K2. And here I also have K1 and K2, and all of them were 1. So when I went to A bar, I changed this one to K1 and this one to K2, the entry itself. So the thing that I get is going to be the sum of all the witnesses. But the sum of all the witnesses is not really useful for me. I want just one witness. Now, of course, again, if for a particular combination of I and j, I had exactly one witness, then I'm getting it, right? So even without this assumption, I can just compute witnesses like this, and then I can go back over this matrix W and just check if the entries make sense, right? So I just look at Wij and I ask, can this be a witness or is it a sum of several witnesses? How do I check it? Well, I just go to that index here and see if I have one in both A and B, right? So even when I'm doing this, for the vertices that are, for the combinations of I and j that had a unique witness, I'm finding that unique witness. But in every other case, I'm not. So now this is the part where we want to use this idea. So here, I want to have a unique witness. Here, I wanted to have a unique white ball. Okay? Somehow try to map this onto that. So let's think of white balls as your witnesses. Okay? So the idea is that I'm going to randomly pick some of the columns of A. And these are like the R balls that I took here randomly. Let's say I take, I don't know, column 2, column 5, column 8, right? And I'm going to say I keep these columns, but outside of these columns, I put everything as 0. Okay? So what am I doing here? I'm just killing witnesses, basically. So if, for example, here I had 2 witnesses for I and j, and when I do this random selection, if only one of them survives, and I turn the other one into a 0, then later on, after I do this multiplication, I would be able to find that witness. Okay? So yeah, that's the algorithm. I just take some columns of A, and I say I only care about these columns. Everything outside of these columns becomes 0. Now I hope that my witnesses have become unique. I then do this thing that I had for unique witnesses, and I find all the unique witnesses. But then I just continue this. Like as long as I have some Cij that is 1, but I don't have a witness for it, I just continue this random process. And every time, I have to also talk about like how many columns I take, but let's not get into it right now. So every time, with this much probability, the witness for ij becomes unique. Because remember, the witnesses were the white balls that we were taking, right? So this is like 1 over some constant. And if I want that probability to go down really fast, I can just repeat the process. I can just repeat this process of taking random columns of A and finding witnesses. Maybe I can do it log n times, then I will get a probability that is 1 over n for not finding the witness. So with probability n minus 1 over n, I will find the witness. Okay, last point here. How should I choose R? So again, look at the one-to-one correspondence that we have between our 2 problems, right? Here we have n balls, and these were basically our n columns, right? And W of them were white. Those are the columns where the witnesses appear, right? And I have to take R balls or R columns, but I have to take it such that this condition is satisfied. But you see, now R depends on W. So in order to decide how many of these columns I want to keep, I have to know how many witnesses I had in the first place, but I don't know that. Right? So how would you solve this? So every R works for some particular values of W. It doesn't work for every value of W. But I don't know how many witnesses I have here. Yeah. So you can, well, the naive thing here would be to just try every possible R. Right? But if you try every possible R, you're trying n values, and then you're doing this multiplication here. So you get n to the power of omega plus 1, which is not good. Right? But actually, you can just try log n different values of R. Because here's the thing. Just look at this part, and let's see what values of W work for any given R. So where is this one? Okay, this is my inequality that I should have. Okay, if I just choose R to be 1, which values of W are already covered? So if I choose R as 1, well, R is 1, so every W between half of n and n is covered. So what if I choose R to be 2? Then I basically have 2W has to be between n over 2 and n. So W itself is between n over 4 and n over 2. What if I choose R to be 3? Then I have n over 8, W n over 4, and so on. Sorry, 4. I don't know why I went with 3, right? So I can just use powers of 2 as my values for my R. And if I try all powers of 2, I will cover all the values of W. So going back to our matrix multiplication problem, even though I don't know how many witnesses I have, I know that the number of witnesses is somewhere between 1 and n. And if I just do these log n different randomized trials, I know that one of them will cover the number of witnesses that I have. So that's what I do. So the overall algorithm is now quite simple. I just take my A and B, and I first set R to 1. I choose one random column of A, and I put everything that is outside of this column to be 0. Then I multiply this column by its index, and then I multiply A bar with B, and I find all the unique witnesses. Then I repeat the same thing, but now choosing 2 columns of A. Then I repeat it again, choosing 4 columns of A, and so on until I have all of A. And this basically finds all of the witnesses for me. Okay? So what is the runtime? The runtime is, well, I have to try log n different values of R. And for every one of them, I was doing n to the power of omega operations. But the probabilistic guarantee that I have here is that each of my witnesses is correct with probability more than 1 over 2e. And if I want this probability to get close to 1, if I want this probability to be n minus 1 over n or something, I have to repeat this whole process again log n times. So my overall runtime gets another log n. So it would be log 2 of n times n to the power of omega. And then after this, I can say that I have every witness correctly with probability more than n minus 1 over n. So the probability that I'm wrong for any one of the witnesses is at most 1 over n, which is very small. Okay. Yeah, so this is all we had time for in this session. But now what I want you to think about until next session is how does this Boolean matrix multiplication and the idea of finding witnesses help us with finding the shortest path? Because that's what we started to solve, and that's why we did all of these things. And actually, the intuition that I can give you, I will formalize this next session, but the intuition is that this witness is basically going to be the index of one of the internal vertices, or actually the first vertex after I. So I want to say whenever I want to go from I to J, I start from I, then I go to the witness of IJ. And then from there, I go to the next witness and so on until I get to J. But the part that is really interesting is how do we define these matrices so that our witnesses really become the next vertices in our shortest path. And that's also the reason why this session, whenever I wanted to say witnesses, sometimes I said vertices, because they're going to be vertices. Okay, so I'll see you next week.